Okay. Any questions before we start the chapter 2? Okay, now we're going to cover chapter 2. Okay, single variable calculus, chapter 2, limit and continuity. Okay, in this chapter, we're going to cover the limit of function and continuity. Okay, most of content in this chapter has been studied during your high school years. So, today we're going to briefly introduce the basic concept of limit and continuity. Okay. Also, recall that the limit plays an important role in the differential and integral calculus. Limit. The goal of this chapter is we discussed limit of functions in general, including a general definition of the limit, and find the limit both numerically and graphically, not only by hand. Yeah. We find limits both numerically and graphically, and we introduce and discuss the concept of one-sided limit. One-sided limit. Okay, here's the general definition of the limit. We write limit f of x when x goes to a is equal to L if we can make the value of f of x arbitrarily close to L by taking x to be sufficiently close to a, but not equal to a. This is important. It doesn't have to be equal to a. X. Close enough, just close enough, not equal to. This notation also can be written in this way. Yeah. F of x goes to L as x goes to a. Okay, here, x is not equal to a is very important. So we made the notice. In the definition, in the general definition of limit, x is not equal to a at all. This means that when defining the limit of f of x as x approaches a, we never consider x is equal to a. So the point x is equal to a does nothing to do with the limit. In fact, f of x need not be defined when x is equal to a. It don't even have to be defined at x equal to a. Okay? So all that matters is how f is defined near a. Near a. Like this. So we can find the limit, we can think of the limit of this function, this curve at a. Even the function looks like this. We may have a hole in here like this. We may not even define it here. Still, we can think the limit of this function at this point, x is equal to a. Okay? All three cases are okay when we think of the limit. One-sided limit. I think this is the first new definition that you may face in college after the high school. Sometimes a function f of x approaches two different limits as x approaches a from the left or from the right. So x like this. X may approach from the left side to a. X may approach to a from the right hand side. We make two different definitions on those two cases. So expression, this is read to the limit, the left hand limit of f of x as x approaches a minus here. So from the left, the smaller part. The right hand limit of f of x as x approaches a equals L. This means this, a plus. X approaches to a from the plus direction, from the right direction. Okay, this is a notation. Okay, both left hand limit and right hand limit are illustrated below like this. So in this, the graph A, we are considering the left limit. In this graph B, we are thinking about the right limit of f of x as x approaches to a plus, like this, okay? That's the notation. Okay, the relationship between limit and one-sided limit is given by the following. Okay. When we say f of x has a limit at x equal to a, or when x approaches to a, that means if and only if, the left limit of f of x is L, and right limit of f of x is L as well. If this equality holds, then we say the limit of f of x is equal to L when x approaches a. That's the definition. So in order to define the limit, we should have two left limit and right limit, both exist and same. Okay. Here are some examples to examine the continuity. You must have heard on Heaviside function. This is the definition of Heaviside function. X is 0, h of x is equal to 0 when x is less than 0, and x is equal to 1, and x is equal to greater than or equal to 0. Then, left limit of h of x when x approaches to a is 0, but right limit of h of x as x approaches to 0 is 1. So, they are not same. Even though left limit exists and right limit exists, but they are not same. So, eventually, h of x has no limit at x is equal to a. This graph shows it. This is such an example. So, this example 2 shows a similar one like this. Determine whether the limit of this function, limit of x over absolute value of x when x goes to 0. Determine whether it exists or not. Think about it at x. Left limit is -1, but right limit is +1. They are not same. So limit does not exist. Okay? Here, next. F of x approaches to L. As x goes to infinity, then y is equal to L is a horizontal asymptote. It's called horizontal asymptote. When x goes to infinity, f of x goes to a certain value. Okay? 점근선이죠. Okay? And if f of x goes to infinity as x goes to a, then we call x is equal to a is a vertical asymptote. The red one. x goes to a, and but h of x goes to infinity like this. Then this is called the asymptote. That is called the vertical asymptote. Red one. Okay, this is the function. Okay, here. Find the vertical and horizontal asymptote of this function, which can be written in this way. This is the graph, the blue ones. And these red and greens are the asymptotic lines of this. Not this one, here. Okay, consider y square minus bx is equal to this, and think about the right limit, the limit at a and minus a on both. Then, if x goes to a, then the limit goes to plus infinity. If x goes to minus a, then limit goes to minus infinity. So, x is equal to plus minus a are two vertical asymptotes. One goes to like this, one goes to here. So we have one here, one goes like this, and this give us this the horizontal asymptote, and this gives us another asymptote like this. So this example shows the meaning of this horizontal and vertical asymptote. Okay, this is a limit law. You know it. You must know this in order to get into the college. Okay. But you may not have seen the proof of this one. Okay, now let's go to this website, which is the proof of this theorem. Okay. The proof of limit laws. Okay. Here you see the theorem that you have seen in my lecture note. And these are the rigorous proof, epsilon delta proof of each of those limit laws. Addition, scalar multiplication, and subtraction, and even, okay, and quotient, reciprocal, and the complex functions. They're all the proof. This has been proved in this way, in mathematical way. Very rigorous epsilon delta proof gives us these theorems. Okay. Okay. So you must know that. I will let you know how to prove it with those epsilon delta argument. That's what you have to learn from chapter 2. That will be your homework. You have to practice a couple of epsilon delta argument proof to pass this chapter. Okay. Next, squeeze theorem. Squeeze theorem. To find the limit, this theorem works very well, which is called as also sandwich property. Okay. Suppose g of x is in between f of x and h of x. Then, when x approaches to a, then we have the following fact. If limit f of x is equal to L when x goes to a, and also limit h of x is equal to L when x approaches to a, then this middle function also should converge to L. That's what it says. So if this g of x function is in between this red and blue one, then this black function should approach to L like those two functions does. Okay. This is called the squeeze theorem or sandwich theorem or just simply sandwich property. Okay. Example 4 shows a good example of such a property. Let's find out the limit of this function. This function. Okay. Okay. The graph of this function is like this. Like this. We want to find the limit of this function when x approaches to 0. What it will be? It's hard to find it by other ways. But we know this function is in between y equal x square and y equal x minus square. So we can apply those sandwich property on this function. Okay, here, this function, the limit of this one does not exist. So we cannot, even though this approaches 0, this limit does not exist. The product of those two functions doesn't mean anything. So the product law cannot be applied here. However, cosine 1 of x and is in between minus 1 and 1. So minus x square, the x square cosine 1 of x is in between this, which is like this. So if we approach it, then x square goes to 0 and minus x square goes to 0 as x approaches to 0. So the middle function also converges to 0 by the squeeze theorem. That's what we can say. So this is a very useful fact that we can use when we talk about the limit. Epsilon delta definition for the limit. Epsilon delta definition for the limit. This is what it says. Okay, I mentioned the real meaning of this epsilon delta argument, which is a kind of microscope in mathematics. Okay, this says an epsilon delta definition is a mathematical definition in which a statement on a real function of one variable, f, having, for example, the form, for all neighborhoods u of y naught, there is a neighborhood v of x naught. such that whenever x is in V, then f of x is in U. This can be written in the following way. For all epsilon which is bigger than 0, there is delta, positive delta, such that whenever absolute value of x minus x naught is in between 0 and delta, then absolute value of x, f of x minus y naught is less than epsilon. These two sentences are equivalent, and this, if function f satisfies it, we can write in this way. The limit f of x is equal to y0 when x approaches x naught. So if function f satisfies this condition, then we can write this. And we call this y naught is the limit of the function at x is equal to x naught. Okay. In the second one, the neighborhood u is replaced by the open interval, and the neighborhood v by the open interval in x-axis and y-axis like this. Okay. Let's see. This graph shows the meaning of the epsilon delta. For arbitrarily chosen epsilon, if the function, in this bar, for arbitrarily chosen epsilon, if we can find the delta that the function is in this box, then we call the limit of the function at A is this value, L. That's what it says. So one is, the epsilon, this is a bar, the same meaning, same meaning. For arbitrarily chosen epsilon, if we can find the delta that make this box contains the function f, then we call this value, L, is a limit of the function f at x is equal to A. This is the same function. Here is the epsilon delta definition of at Wolfram alpha, and here is a YouTube explanation of the epsilon alpha definition. Okay, you may take a look, and this is the epsilon delta definition, like what you see, the same thing, and also you can watch the YouTube explanation of epsilon.
Let me draw a function that would be interesting to take a limit of.
Yeah,
and I'll just draw it visually for now, and then we'll do some specific examples a little later. So that's my y-axis, and that's my x-axis. And let's say the function looks something like, I'll make it a fairly straightforward function. Let's say it's a line for the most part. Let's say it looks just like that, except it has a hole at some point x is equal to A. So it's undefined there. And let me black that point out just so you can see that it's not defined there. And that point there is x is equal to A. This is the x-axis. This is the y is equal to f of x axis. Or let's just say that's the y-axis. And let's say that this is f of x, or this is y is equal to f of x. Now, we've done a bunch of videos on limits, and I think you have an intuition on this. If I were to say, what is the limit as x approaches A? And let's say that this point right here is L. We know from our previous videos that, well, first of all, I could write it down. Let's see, the limit as x approaches A of f of x. What this means intuitively is as we approach A from either side, right, as we approach it from that side, what does f of x approach, right? So when x is here, f of x is here, is right there. When x is here, f of x is there. And as we see that it's approaching this L right there, right, when you approach from that side. And then when we approach A from that side, right, and we've done limits where you approach from only the left or the right side, but to actually have a limit, it has to approach the same thing from the positive direction and the negative direction. But as you go from there, if you pick this x, then this is f of x. F of x is right there. If x gets here, then it goes here. And as we see, as we get closer and closer to A, f of x approaches this point L, right, or this value L. So we say that the limit of f of x as x approaches A is equal to L. And I think we have that intuition. But this was not a very it's actually not rigorous at all in terms of being specific in terms of what we mean as a limit. You know, all I've said so far is as we get x gets closer, what does f of x get closer to? So, in this video, we will attempt to explain to you a definition of a limit that has a little bit more, or actually a lot more, mathematical rigor than just saying, you know, as x gets closer to this value, what does f of x get closer to? And the way I think about it, it's kind of like a little game. The definition is, so if this means, this statement right here means that if you want to, that I can always give you a range about this point. I can always give you a range. And when I talk about range, I'm not talking about it in the whole domain range aspect. I'm just talking about a range like a, you know, as long as I'm no further than, I can give you a distance from f of x will always be at least that close. This would be L minus epsilon range. And if you think about it, this makes 1.
So,
right? So we're saying that the limit
for any arbitrary
x approaches 1 of f of x, I haven't defined f of x, but it looks like a line with a hole right there,
this
is equal to 2. This means that you can give me any number. Let's say you want to try it out for a couple of examples. Let's say you say, I want f of x to be within point. Let me do a different color.
So
I want f of x to be.
So yeah, you can now have the information to understand the meaning of it. So I will give you some examples how to really adapt those arguments on problems. Okay, use the above definition to prove this function. What's the limit? What's the limit of 3x minus 2 when x approaches 2? Okay, so we can guess it is a 4. So when L is equal to 4, so for an arbitrarily chosen epsilon, all we have to do is find a number delta such that 3x minus 2 minus 4 is less than epsilon. Okay, so all we need to is find this delta value when absolute value of x minus 2 is less than delta, then this one satisfies. In order to do that, all we have to do is start from here. 3x minus 2 minus 4. Okay, simplify. Then 3x minus 2 minus 4 is 3x minus 6, which is 3 times absolute value of x minus 2. So whenever this value is less than delta, then we can make this one less than epsilon. How? So how can we do that? So we make a relationship between this epsilon and delta. Okay? So if in order to be this one is less than epsilon, when absolute value of x minus 2 is less than delta, then just choose delta as divide delta, make it small enough. So since there's a multiple of 3 here, so you just divide this number on here. So choose delta as epsilon over 3, like this. Then, let's say, if absolute value of x minus 2 is between 0 and delta, which is epsilon over 3, then start from here, and you have this one. But this is less than epsilon over 3, which replaces this value. Then this will be cancelled each other to leave the epsilon here. So what this says is, if we, for any arbitrarily small epsilon, if we choose delta as 1/3 of epsilon, then it always, this value is less than epsilon. That's what it says. This method works for all problems. So all you have to do is just let arbitrarily small epsilon, then start from here to simplify it to make a relationship with this given one, and then choose delta cleverly. If you make this one as epsilon over 5, it still works. You can make it small enough. You can make epsilon over 100 as well as a delta. Okay. So if for any epsilon, if delta is epsilon over 3 or less, then whenever this is hold, this is true. So the limit exists, and the limit of this function at that point is 4. That's what it says. That's the proof. So basically, proof is very simple. So limit law, sum law. If f of x is equal to L, the limit of f of x is equal to L, limit of g of x is equal to M, and both exist. This is important. Both exist. Then the limit of the addition of those two functions are addition of L and M. Okay. How can you prove it? Okay, now we're gonna give a proof once more on this epsilon delta proof on the limit law, sum law. Okay, for a given epsilon, all we have to do is to find a delta, positive delta, such that whenever absolute value of x minus a is in 0 and delta, then f of x plus g of x minus L plus M is less than epsilon. Then using the triangular inequality, we can rewrite this one in this way with the inequality here and this. As you see, this and this is related to the limit of f of x and limit of g of x. We know these limits both exist. So, we can, for any arbitrary small epsilon or epsilon over 2, there exists a delta 1 such that absolute value of x minus a is less than, is in 0 and delta 1, then f of x minus a is less than epsilon over 2. For this small value, we can find delta 1. Similarly, since the limit of g of x does exist, so there is, for arbitrary small number, there exists a number delta 2, such that if this value x minus is between 0 and delta 2, then g of x minus m absolute value is less than epsilon over 2. So, now we choose delta as a minimum of those two, delta 1 and delta 2. Then, if absolute value of x minus a is in 0 and delta, then that satisfies this one and this one. This condition gives us this. This condition gives us this. So, both all together, this can be written as this one, and that condition, this is less than or epsilon over 2, and this one is less than or epsilon over 2. So, the addition makes it epsilon. So, for this delta that we have chosen, there exists, for arbitrary small epsilon, there exists a delta that makes, if this is true, then this is true, which makes the limit of f of x plus g of x is equal to L plus M. That's what it says. Here's one more example. Prove this, the limit of this one is 0. So for arbitrary chosen epsilon, so this is f of x is square root of x, and L is equal to 0. So, and x approaches to 0 here. So we now all set. So epsilon, for arbitrarily small epsilon, positive epsilon, and all we have to do is find the delta such that if x is in 0 and is between 0 and delta, then square root of x minus 0 is less than epsilon. So, in order to make a connection from here to this condition, so just make a square out of those on both sides, squaring both sides of the inequality here. Then square root of x is less than epsilon. We have it from here. Then we have x is less than epsilon square. Whenever x is in between 0 and delta. So, for this condition, we want to have this. But, all we have to do is just squaring it. Then we have this condition. X is less than epsilon square. So all we have to do is just to choose delta as a epsilon square. Then, it's all done. For arbitrary epsilon, if delta is chosen as epsilon square, then square root of x minus 0, which is the square root of x, is always less than epsilon. Because x is less than epsilon square, x square root of x must be less than epsilon. You know what I mean? Okay. So this is the proof. It's a very simple idea, and just you need to be a little bit clever to find the relationship between those two. If this is true, then this should be true. How we decide delta? So squaring those sides to make x square and epsilon square. So epsilon square should, if epsilon square is equal to delta, then this same equality holds. That's what it says. I have made the YAP here, so which shows the epsilon delta algorithm here. This function x square minus x over x minus 1. So we may think this is x times x minus 1. So this is right. So this is same as y is equal to x when the function is undefined at x is equal to 1 here. So here so the limit when x goes to 1, it approaches to 1. So L is equal to 1 here. So when x is, when A approaches 1, and let's make epsilon, small epsilon 1. We can choose even the smaller one here like this. Then we have a small epsilon here, but we can always find the delta to make it, this function is in this box. We can even make, if we choose very small, like this, all we have to do is find a reasonable delta value to make the function is inside of this block. This is what I wrote in here. So you may exercise some of the examples that you're going to see in the exercise problems. Put it in here and use this applet. Read it. We may make some changes in here to make a change. But here, for example, if we give a different function at x cube minus here, then let's see what happened. Let's see what happened. Evaluate it with the given different function. Let's see what will happen. Let's think about the now what is going to be the limit of this function. Then let's find the a. 그러면 이런 경우에 a가 뭐가 되지? x가 1로 갈 때 x가 이게 1이 아니지. 이런 경우에 자 생각해 봅시다. Okay, now this, if we change the function like this, then the function that we have is x square, like this. So, when x goes to a, the value is 1. So, L is 1. So, that's right. Then, let's make it as a very small one, like this. Then, let's find out the delta here. That's all we have to do. As you see here, this, okay, so that's x minimum minus 1 to, for example, to 0 to here. Okay, let's evaluate it once again to make the different function here. And make something here. And change it, the epsilon value as a very small one. If we can find a delta value, then we, okay, that's right. It is in here. As you see here, this, at this value, when x is equal to 1, when x approaches to 1, the value of the function goes to 1 that shows the function has the limit at when x goes to 1 here. That's, this simulation tool will be revised to make this red dot in here soon. Okay. let me know. Anyway, just practice those to find what you like to understand what it is. And here is the homework problems that from the exercise in section 2.1 to practice this epsilon delta argument for the limit. I suggest you to do at least a couple of them to understand what it is. And the next definition is the precise definition of the infinite limit. Infinite limit. If f of x goes to infinity, the limit of f of x is infinity means there is a positive number delta. If there is a positive number delta, then even though what this means is for every positive number m, if we can find the positive number delta that makes if this value is in between 0 and delta, then f of x is equal bigger than m. Then we say the limit is infinity. This is what it says. But this means for every positive number m, we can find the delta that makes this function is bigger than that number. That means this function value is very big, really big. It can be far ahead of the number that we can find. So that means the limit of this function is limit. This is what it says. Okay. For arbitrarily chosen big number m, if we can find the delta that makes f of x is bigger than m, whenever absolute value of x minus a is in 0 and delta, then that's the formal definition of the infinity. Let's use this definition of infinite limit on the example 8. Show the limit of 1 over x squared is infinity. You know the graph of this one. Okay. For any large number m, let's find out delta that makes this function is bigger than m. Fine. Think about it. Let's find the delta that makes this. Okay. So since both m and x squares are positive, we can think from this condition, we can think x squared is less than equal to 1 over m whenever absolute value of x is in between 0 and delta. So taking the square root of both sides, so square root of x squared is absolute value of x, then absolute value of x is less than or equal to 1 over square root of m whenever absolute value of x is in 0 and delta. So from this computation, we can say for any positive number m, if we choose delta is equal to 1 over square root of m, then absolute value of x, then 1 over x squared is always bigger than m whenever absolute value of x minus 0 is in between 0 and delta. That's what it says. So, this example shows the standard technique to find a delta to show a function which has an infinite limit. Example 9 shows the following, find the following limit or explain why the limit does not exist. Okay, how are you going to explain it? Okay. Limit does not exist. Indefinite. For example, if you delete it, then indefinite. So if you draw, this is what you see. This is a function that asking. So when x approaches it, how it behave inside here? It's just up and down, and the limit is varies from positive value and negative value. If we can make it as very small, then we will have this. If you make it a little wider, then Then it will build something like this. So you can what, magnify or simplify the graph. And from here, what you see is it vibrate. It vibrates. So the limit does not exist. As you see, it comes from 1 and -1. It just changes the values when x approaches to 0. So this simulates the limit does not exist because it diverges. It varies as x goes to 0. Okay, and what else? Example 10. Plot the graph of the function near 0 and check if the left-hand limit, right-hand limit, and limit at x equals 0 exist. Let's see. This is a graph of the function, and let's see then how it works. Okay, this is indefinite, and you can see the graph can be. Is this same thing? Absolute value of x. Is it? Is it? Is this value? No. A cosine? Is it? This may not be the right. Cosine 1 over epsilon. This is different one. I made a wrong copy of it. In this case, yeah, I can copy this command to draw this graph. Okay. Anyway, as you see, this graph is a step function like this. So right limit is 1/2, and limit is -1/2. As you see, this is the sign values and absolute sign value, and then so the left limit and right limits are different. So the limit is undefined. Okay, so find the left limit and right limit, and the limit does not exist. That's what the answer says. Here's the exercise on section 2.1. From here, you will see lots of problems, and you may try to use the solutions here and the applets here to solve the other problems as well. Okay. You may manipulate those in here or at the Math1 server to make your record to submit it. Okay, and this is in here for sine and cosine function. This composite function, the graph of this one is like this. So from here you can find the vertical asymptote exists here and there. And from here, you can use a Squeeze theorem to prove the limit of this function at x is equal to 0 is this value. Okay, let's see here. Then you will see the limit is equal to 1. And when x goes to 0, the limit of the function is equal to 1. And what else? Epsilon argument. Here's the epsilon delta argument. And also, this is another Sage cell that you can use here. You can use a Sage command here and plot. And then you can evaluate it, the value like this. This is another new version that you can use. We can do the same thing and with a different function, cosine x here, like this. Cosine x function. Then we want to find the limit when x is equal to 1. Then limit cosine x. Oh, this x, yeah, this parenthesis. Then we can find 1. When x is equal to 1, then we have the limit of cosine x when x goes to 1. That's the value. Something like that. This is another server that we are developing. And also YouTube explanation of those things. And next section is continuity. We now introduce the continuity, including types of continuity and one side's continuity and continuity on an interval. And categories of the continuous function, and mainly the intermediate value theorem. Do you have a question so far? So, tomorrow we're going to cover the section 2.2 to clear up chapter 2. So, you may go look over the exercise problems at the end of chapter 2 here and try to solve one or two problems of your choice in each section and upload it in Q&A and then make collections each others to finalize solution. That's your homework to do on chapter 2. Okay, I think now it's the time to wrap up the class and we will continue the section 2.2 tomorrow. Okay, any questions? Then class dismissed. Okay.